A very good morning to one and all. I, Dr. Ribhuabsan Panda, want to discuss about a very important topic, that is floating point representation. Floating point representation is a very important topic in digital electronics. There are many concepts, many chapters in the digital electronics, and this is one of the most important chapter in the digital electronics. So let me write the floating point representation. Now in this, there are three words, floating point and representation. We all are well acquainted with the third word, that is representation. Whenever you are showing something in a proper way, then that is called as representation. Whenever you are notifying something in a proper way, that is called as representation. But the new words are floating point. Before going for this floating point, let me tell you what is fixed point. Okay, so there is another important word that is called as fixed point. So we all are well acquainted with the decimal values or the numbers which are represented with the decimal point. Now if the decimal point is fixed, then that particular representation is called as fixed point representation. For an example, I am writing 302.52. The decimal point here is fixed. That means there is no alteration, there is no variation of this decimal point. That's why it is called as fixed point representation. But if we are able to move the decimal point, if the decimal point can be moved from one place to another place, then it is called as floating point representation. Now we will come to know about the floating point, which means the decimal point can be moved from one point to another. That is called as floating point representation. Float, जिसको हम हिंदी में तैरना कहते हैं, means what? Moving from one place to another. So similar analogy can be applied here. Floating point representation means the decimal point can be moved from one point to another. For an example, I am writing floating point. And I am giving the same number 302.52. Now here the decimal point cannot be moved, but if I move this decimal point, then I can tell that this is floating point representation. How can I do it? Suppose I will move this decimal point towards the left. That means I am writing 30.252 into 10 to the power 1. So this 302.52 is similar to the 30.252 into 10 to the power 1. That means this particular decimal point is shifted one place and we are multiplying a power of 1 of 10. That meaning is same. That means this is also 302.52. This is also, finally we will get 302.52. So this type of representation is called as floating point representation. Now there is a standard given by IEEE, and that standard IEEE 754 has been followed for this floating point representation. The standard is given around 1985, and from that it has been followed. IEEE standard means set of rules or set of protocols that we have to follow for certain devices or certain kind of representation or certain kind of process, and that has been given by IEEE 754. So this IEEE 754 standard has been followed for representing this floating point numbers, and around 1985 these numbers have been represented. Means that particular standard has been followed for representing this floating point representation. So till now what we have understood? We have understood that there are two types of representation. One is fixed point, another one is floating point. Fixed point means decimal point is fixed, we cannot move. Floating point means the decimal point can be moved. This type of representation is called as floating point. Float means to move from one place to another. Now let us discuss about the normalized form. The next topic which we are going to discuss in this floating point representation is normalized form. So let me write one number. I am writing one number 30152.68. I am writing a decimal number that is 30152.68 and that is given with a decimal point before the 68. Now I can represent this number by keeping at least one non-zero digit before the decimal. So I can represent this by keeping one non-zero digit before the decimal. So I am shifting this decimal 1, 2, 3, 4. So 1, 2, 3, then 4. 4 points have been shifted. Then I can write 3.015268 multiplied by 10 to the power 4. I can represent like this. So this is now called as normalized form. So what is normalized form? Normalized form is a form where the decimal point is shifted in such a way that there should be one non-zero digit before the decimal. That means the decimal point is shifted now four steps or four positions. Then we will get one particular non-zero value before the decimal, and that is known as normalized form. So normalized form is a form which is represented as one non-zero value before the decimal, and after the decimal there may be many numbers, and this type of form is very important in this particular floating point representation. We will discuss how one particular form or how one particular number can be represented in this floating point representation. So till now I have written all the decimal numbers. In the similar manner, I can write the binary numbers. For an example, I am writing 1011.11. This is a binary number. Now I can represent this as a floating point number by shifting this decimal value. So I can write this decimal value can be shifted one position, second position and third position to get the normalized form. So 1.01111 multiplied by 2 to the power 3 now, because 3 positions have been shifted. 1, 2, then 3. 3 positions have been shifted. So I have to multiply 2 to the power 3 because this is a binary number. This is a binary number. Till now I have written all the decimal numbers. Same thing can be applied for the binary number. So this representation is in the normalized form for this binary number. This representation is in the normalized form for the decimal number. So any kind of binary number I can represent in the normalized form. So till now we have discussed what is floating point, what is fixed point, what is normalized form. Now we will discuss how we can represent a particular number in floating point. So all of you, please pay attention. Now we will go for the core part of this floating point representation. How we can represent a particular number in this unique representation. So let me write a particular number and then we will find how it can be represented in the floating point representation. So at first I am writing 347.625 and I am writing this in the decimal. We all know how to convert a decimal number to the binary. Simple example I am giving. If you have forgotten that, you can remember that and you can analyze. Suppose I am writing a number 13 in the decimal. How can you represent in the binary? Here I am writing 10, which is the base. Decimal, the base is 10. Binary, the base is 2. So for the decimal number I can write like this and I can divide by 2. So 2 multiplied by 6 is 12, remainder is 1. 2 multiplied by 3 equals to 6, remainder is 0. 2 multiplied by 1 is 2, then remainder is 1. 2 multiplied by 0, that is 0 and the remainder is 1. So from the bottom to top you have to move. So like this you have to represent a binary number, represent a decimal number in terms of binary. So I can write this 13 base 10 equals to 1101 base 2. 13 base 10 is equals to 1101 base 2. Similarly, for a decimal value, I can represent like this. Suppose I am writing 0.25, then I can multiply with 2. Okay, then I can multiply with 2. What I am getting? 0.50. You just concentrate on the value which is before the decimal. So that is 0. Okay, then remove all these values and keep only 0. So if I remove this 0 from 0, so it will remain as 0 only. So 0.50 multiplied by again 2. So I am getting 1.00. Now I can go from top to bottom because after the decimal the values become 0 now. After the decimal the values become 0 now. So no need to go further. So I can go 0, 1. So 0.25 in the decimal can be represented as 0.01 in the binary. So from the top to bottom you have to go. This is basically the conversion from decimal number to the binary number. You already have studied this, you already know this. In case anyone has forgotten this, then I just request that person that you please see this particular thing and you try to remember how to convert a decimal value to the binary. Anyway, this is the process by which you can convert a decimal value to the binary. Now here I have written one decimal number. Here I have written one decimal number. Now I have to convert this decimal number to the binary number first. So I am just writing after conversion I will get this binary number 101.011.101, that is binary number. So first step we have done, that is representing this decimal number in terms of the binary number. Then very important thing, we have to convert this particular representation in terms of floating point. But before going for that, we have to understand how many floating point representations are there. There are basically three types of floating point representation. One is single precision, second one is double precision, third one is extended precision. First one is single precision, second one is double precision, third one is extended precision. In the single precision there is one unique format, in the double precision there is one unique format, in the extended precision there is one unique format. So we will concentrate at first about the single precision. We will concentrate about the single precision first. So in the single precision there are three parts. First one is sign, second one is exponent, third one is mantissa. Okay, first one is sign, second one is exponent, third one is mantissa. This mantissa is also called as significant, or it can also be called as fraction. Okay, so in this single precision format there are three parts. In the double precision format also these three parts will be there. Extended precision format also these three parts will be there, but the bits will change. change. So let us concentrate on the single precision format only, and after this we will discuss about the double precision as well as the extended precision. So in the single precision format, we will go for these three parts. One is sine, then exponent, then mantissa. Okay. In this single precision format, the total number of bits we are dealing with, that is 32. How it is divided? For sine, 1 bit. For exponent, it is 8 bit. So 1 plus 8, it already became 9. So remaining is 23 bit. So it's 8 bits. Now this one is 23 bits. So to represent the sign of the number, we'll just use 1 bit. To represent the exponent of the number, we'll use 8 bits. To represent the mantissa or the fraction or the significand of the number, we'll use 23 bits. So this is basically the single precision format which we are following. All these have been given by IEEE standards, and that IEEE standard has been followed all over the world. It's not like that one country will follow one format, another country will follow another format. All over the world, this particular format has been followed. That is given by this IEEE standard. So the single precision format represents three parts. Again I am repeating: sine, exponent, mantissa. Sine will include 1 bit, exponent will include 8 bit, then mantissa will include 23 bits. So this is the basic step or the fundamental thing which we have to remember when we are going for this floating point representation. Whenever we are going for this floating point representation. Now my dear students, how I will represent this particular point into this floating point representation? First step is to determine the sign of the number. Here I have not written anything, plus or minus. So generally we will take this one as the positive number. So this one is also we will consider as the positive number. So beside this means just at this part of this whiteboard I am writing the steps, and at this part of the whiteboard I will analyze, I will tell you how to represent this number. So here I am writing the steps. So the first step to determine the sign of the number. First step is to determine the sign of the number. Here the sign of the number is positive because nothing has been mentioned. If I could have mentioned minus sign here, it would have been negative. But nothing has been mentioned means this is a positive number. So second point we have to remember, for positive number it is given as 0, and for negative number it is given as 1. So 0 is considered for the sign bit when the number is positive. When the number is positive, and 1 is considered for the sign bit when the number is negative. 1 is considered for the sign bit when the number is negative. These are the two steps at first you have to follow to determine the sign of the number at first. Then 0 is considered if it is a positive number, 1 is considered if it is a negative number. So it is a positive number, so the sign bit is 0. So here I am writing the sign bit is 0. So at first, in the first part, we have to write the sign bit. Now here you can see you have already converted this particular number to the binary. Whatever number is given, you have already converted this particular number to the binary. So if directly binary number is given, no need to convert. If any other number like decimal number, octal number, hexadecimal number is given, you have to convert to the binary. So I am including this particular step which I have already done at the beginning in the step 3. So convert the number to the binary. So whatever may be the case, decimal, octal, hexadecimal, you have to convert into the binary. All this conversion already you have studied. If you have not studied, then you can go for any kind of book or any kind of internet source and you can see how the conversion has been taken into consideration. I will try to give a full video about this conversion from one number system to another number system. Anyway, the third step is convert the number to the binary. Any type of number system it is given, you have to convert the number to the binary. Already we have done at the beginning. Now the fourth step, that is bring the number to the normalized form. The fourth step which I am writing, bring the number to the normalized form. Bring the number to the normalized form. So this is the fourth step which we are going for, that is we have to bring the number to the normalized form. What is normalized form? I have already told earlier that at least one non-zero value, not at least one non-zero value should be before the decimal point. Okay. So this is the binary number. I am writing 10 10 110 11 101 011 011 0.101. So this is the binary number I am writing, and that I have to bring to the normalized form. Remember my dear students, whenever you are shifting the decimal point towards the left, suppose I am standing here and I am writing like this, whenever I am shifting the decimal point towards the left, then the power of the 2 is positive. Whenever you are shifting towards right, then the power of the 2 will be negative. This is an obvious thing, this is a common sense, but still you have to remember this. Whenever I am shifting the decimal point towards the left, obviously the power will be positive. So I am shifting this. How many positions I have to shift? Let's see. 1, 2, 3, 4, 5, 6, 7 and 8. So I can write 1.01011 101 multiplied by 2 to the power 8. Now we have found out the normalized form. Now we have found out the normalized form. The normalized form, the fourth step already we have got. Now the fifth step, to calculate the exponent. Remember my dear students, for a single precision format, any unsigned number from -127 to 127 or any signed number from 1 to 254 can be represented for single precision format. Okay, for this particular single precision format, any number which is signed, that is -120 -126 to 127 -126 to 127, then 1 to 254, that particular numbers can be represented in this single precision format. Okay, in this single precision format, these numbers can be represented. Now, as I told, this is the way of representing the range of the single precision format. Then ultimately I have to add a value to the power of the 2 to get the exponent. So the next step is, here the space is less, so I am writing, let me write the steps here. So I am writing the steps, the further steps here. The step number 5, Step number 5. Steps. So step number 5, that is I am writing. Which one is to find out the exponent. To find out the exponent, add 127. This 127 we have to add 127 to the power of 2. To the power of 2 that has been find out, that has been determined, after the normalized form. Okay, so we have to add 127 to the power of 2, which has been determined after the normalized form, means after getting the normalized form. So here I am writing after getting the normalized form. So this is the normalized form. After getting the normalized form, what we have found? The power of 2, that is 8. So exponent I can calculate by adding 127 plus 8. The power of 2 is 8. Now I have to add 127. What is the value? That is 135. But this is in the decimal form. Remember this, very important. This is in the decimal form. After this step, we can go for the next step. That is step number 6. Convert the exponent. Which is in the decimal form. To binary. So this 135 should be converted to binary. So let us convert this 135. So if you convert this 135, how much you will get? So let me convert this 135. Here I am writing 2. So this will be 6, 1, 5, then 7, remainder is 1. Then 2, that will be 3, and that will be 3, remainder is 1. Then again 2, that will be 1, and this one will be 1, 3. So 6, remainder is 1. Then 16, 2, this is 8, remainder is 0. Then 2, it is 4, remainder is 0. Then 2, it is 2, remainder is 0. Then 2, it is 1, remainder is 0. Then finally 1, it is 2. Then remainder is value is 0 and remainder is 1. So 1, 0, 0, 0, 0, 1, 1, 1. This is the conversion. Already you know how to convert. Still I have written. So now I will write this one is equal to 1, 0, 0, 0, 0, 1, 1, 1 in the binary form. Already we have converted. The sixth step is over. Now my dear students, this particular value after the decimal is called as multiplication. These numbers after the decimal is called as multiplication. So let me write the seventh step. So this space is not enough. So let me write the seventh step here. So I hope you can understand, because at one point I could not able to, at one place I could not able to write. So I am writing the step number 7 here. I am giving the number 7 means it is the step number 7. So here the numbers which are there after the decimal in the normalized form is called as multiplication. Numbers, or you can tell the bits. Instead of writing the numbers, you can write the binary values of the bits. Okay, the string of the bits. After the decimal point in the normalized form, is Mantisha. After the decimal form, whatever may be the string of the bits, that is called as Mantisha. So these all are now Mantisha. Exponent we got in the binary value, that is step number 6, and the step number 7 is whatever may be there after this decimal value, that is known as Mantisha. So we got the Mantisha. Then the final step is, you might have observed in the single precision format, sign bit 0, that is 1 bit, exponent we got this value, that is 8 bit, and the Mantisha, that is 23 bits. But here how many bits are there? 0, 1, 0, 1, 1, 0, 1, 1, 1, 0, 1. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 bits are here. So what we have to do? We have to add the remaining number of zeros to get this 23 bit in the Mantisha. How we will add? To the right hand side. Okay, that is the last step. So add zeros to the right side of the Mantisha up to 23 bits. Means whenever you are getting the 23 bits as the Mantisha, you have to add the 0. So up to 23 bits, you have to add the zeros in the Mantisha. This is the final step, or this is the 8th step. So let us write how this final floating point representation is associated with this number. So sign bit is 1 bit, sign bit. So let me write in another color so that it will be prominently visible. So let me write in red. So the sign bit is 0 because it is a positive number. Sign bit is 0. This is a positive number. Then the exponent is having 8 bits. So the exponent is having 8 bits. So directly I can write this binary value, that is 1 0 0 0 0, 1 4 zeros, then 1 1 1. So it is having 8 bits. So this is 1 bit, this is 8 bit. Sign bit, exponent over. Then Mantisha, this one I am writing 0. Whatever may be there after the decimal value. Step number 7. So 0 1 0, 1 1 0. 0 1 0 1 1 0 1 1 1 0 1 1 1 1 0 1. So this is the Mantisha we have written, but this is not the final Mantisha. How we have to do now? We have to add the zeros unless and until it is 23 bits. So 1 2 3 4 5 6 7 8 9 10 11. 11 bits already we got. Then 12 number of zeros we have to add. So 1 2 3 4 5 6 7 8 9 10 11 12. So 12 number of bits we have added, and finally we got the Mantisha. So this 347.625 decimal number is now represented in single precision floating point. So this is all about the floating point representation. You can remember these steps, and any value if it is given, you can follow these steps and you can represent that number as the floating point representation. Generally in the semester 5 mark questions are coming. Sometimes some bit questions may come, sometimes some objective type of question also may come. So this is one of the most important topic So I hope all of you have understood the single precision format representation in the floating point. Okay. So basically 347.625 is represented in the single precision format in this floating point representation. So at last I want to tell one motivational quote and I will end this class. So please remember this very nice quote which is very close to my heart. अगर तुम दिल की सुनते हो और दिमाग से सोचते हो तो समझ लो सुधर गए हो. अगर तुम दिल की सुनते हो और दिमाग से सोचते हो तो समझ लो सुधर गए हो. और अगर लोग तुम्हारे खिलाफ बोलने लगे तो समझ लो तरक्की कर रहे हो. Thank you all of you. Have a very nice day. Namaskar.